All right, so we will be talking about the interaction between atoms and light. Now, things that we're going to be talking about today are things that you need to know for the rest of the class, for the rest of the semester, because we're going to be using this stuff that we're going to be talking today to explain everything, to explain the stars, to explain galaxies, to explain the existence of the entire universe. All that is going to be explained in terms of things that are really, really tiny, what we call modern physics. Modern physics has to do with light, with atoms, quantum physics. That's all it is. All right, so here is a single proton. A single proton is called an atom. In fact, this is a hydrogen atom. So one proton is an atom. You don't need electrons, you don't need neutrons. Single proton, hydrogen atom. That's all it is. So this is a positive proton here. There's also negative protons. They're called antimatter to the proton. And they exist. They exist. And they use them in Switzerland to collide them with, it's called a collider. They use the protons with a negative charge, the antiparticle, the antiproton, with a proton. When they collide, enormous amounts of energy comes out. But the atoms that we are used to in this universe, the atoms that you're made of, I'm made of, my dog is made of, those are all positive protons. So a single positive proton is a hydrogen atom. Now around here, there are certain orbits. These orbits are very, very specific. They're made by God himself, all right? So electrons can exist in these orbits. And if you have one single electron, normally that's one single electron goes to the lowest orbit, the one that is closest to the proton itself. This is called the ground state. So the number one level, number one orbit, number one state is called the ground state. Here, the electron will have its lowest amount of energy. Why is that? It's because the electrons and protons, they attract each other. Electrons have a positive charge, electrons have a negative charge, protons have a positive charge, so they attract each other. The closer they are, the more attraction. And so when it's in the ground state, the electron can't move around very easily. The higher the state, the more free the electron feels from the power of this positive negative interaction. So here in this case, the electron stuck in the ground state. When the electron goes in a higher state, it always comes back down as long as there's room here in the ground state. Everything, all the electrons tend to come down to the ground state eventually. They do it pretty fast in electron time. In our time, be extremely fast. I'm not sure what the electron thinks though. All right, so the electrons can go higher up if they have more energy. So where would they get energy? Photons. Photons are pure energy. So they can absorb a photon and go to a higher orbit. If there is a photon that is exactly the right kind of energy. So if there is a photon that comes in with the energy difference between the third and the, let's see, what do we got here? The second and the third orbit, then the electron goes to the next orbit. All it needs is the energy that is the difference between the second and the third orbit. So a photon that comes in that has that property, it goes high. However, if it doesn't, then it can't happen. You can't just go in between the orbits. That's not an okay thing. The electron will never end up there. Electron will never end up there. Only in whole orbits. That's all there is to it. Only in whole orbits. Now, the higher the orbits, the more energy the electron has. So higher orbits, electrons are very energetic. In fact, we call them excited. So when the electron is excited, it's in the higher orbits, not in the ground state. So ground state, electrons are kind of wimpy. As they go up higher and higher, they get more and more energy. And we say excited atoms or electrons not in the ground state. So if you're an atom and you don't have electrons in the ground state, the electrons in higher state, we say you're an excited atom. So if you have an electron in the ground state and you have a proton, we say you're neutral. You're not excited. You're just a neutral atom. You're not very exciting. So here we have one that is not excited. We call this a neutral hydrogen atom. Why do we call it neutral? Because the charge of the electron and the charge of the proton are identical but opposite. So they're equal to each other. And so they cancel each other out. So the negative charge of the electron, the positive charge of the proton, cancel each other out. We get a neutral hydrogen atom in this case. Remember, one proton, hydrogen. This does not have an electron at all, no electrons. We say this is an ion because we just have a positive charge. So we say this is a positive hydrogen ion. Ions are atoms that have charge. So this one has got a positive charge. There is no electrons here to make it neutral. Ions are charged atoms. Here's another charged atom. This one is a negative hydrogen ion. It's got 2 electrons, 1 proton. So this one is negatively charged. We say negative hydrogen ion. Now the electrons have 1,000th the mass of the protons, but exactly the same amount of charge. All right, so here's a photon coming by. This photon has energy, all right, but it's not exactly the right energy. If this if this photon had enough energy to take this electron to an exact orbit, like from here to here, then that would happen. If it had just as much energy to take it from here to here, that would happen. But if this energy was to take it over here, it would not happen. In between orbits are not allowed. Only whole orbits are allowed. So here, the electron is bouncing off the photon because it's not the right kind of photon. They don't like each other. But the direction is changing. So the photon is coming this way. If the electron wasn't here, it'll continue going this way. Because the electron is here, the electron changes the direction. And that's it. Just the direction of the photon changes. We call that scattering of light. A tiny, tiny, tiny amount of energy is lost. It's inconsequential. So basically the same photon that is going this way, now it's going this way. Only the direction is changing. This is called scattering. Now, is there an example for scattering? It's the biggest example I can give you. If you have a sky on top of your head, the color of the sky, the blue color of the sky, is a very good example of scattering of light. The sky is blue because the electrons in our atmosphere, they scatter the light, the blue light of the sun, and hence you see a blue sky. So this is the cause of the blue sky. Now this one here is very specific. See what's going on here is a photon with 94 nanometer energy is coming in. This is an ultraviolet photon. This time, the electron likes this one. It takes it all the way to the 4th orbit. And then from the 4th orbit, the electron is coming down to the 3rd, to the 2nd, and to the 1st. Each time the electron comes down in orbit, it's losing energy. So it gives off a photon. Here, an infrared photon. Here, a red photon. Here, an ultraviolet photon. If we add up the photons that we get here, there's 3 photons that we get here. 1, 2, 3. The energy of those 3 photons equals the energy of the photon that was absorbed to begin with. So this guy here, its energy is equal to energy of all these 3. So this guy has disappeared. The 94 nanometer photon, gone, no longer exists. In its place, we have 3 different photons. So that one photon became 3 photons. Doesn't necessarily have to happen this way. It could have gone all the way to the 4th, came all the way from the 4th to the 1st again, or maybe gone from the fourth to the first, fourth to the second, fourth, you know, it could have done entirely different things, like from the third to the first. So this is just an example of what could happen. I give you a very, very specific example that actually does happen. This is the absorption of light. So if you get a spectrum of light, this photon's position will not exist. It'll be a dark line here. You won't see this light of ultraviolet at 94 nanometer photon. So we also have a spectrum of not just light, but ultraviolet. So when you get the spectrum of ultraviolet, there'll be a black line where this photon should exist, where this 94 nanometer photon should be. Its absence tells us something's happened to it. It got absorbed. This is the absorption of light. Okay, I don't know why this doesn't happen in the first shot. This is called collisional excitation. So what happens here is there's two atoms here. They both have an electron. They two collide. Once they collide, the energy of the collision goes into the electron. The electron takes the energy of the collision, goes up in orbit, comes back down, and emits a photon. Now, one photon matches this, one photon matches this. The red light happens when the electron in the hydrogen atom goes from the third to the second. It gives you this beautiful red light. When the electron comes down from the fourth orbit to the second orbit, it gives you this beautiful, whatever light this is. What is this light, you guys? What color is this? It's not green, it's not blue, it's
turquoise.
Turquoise. Thank you. Yes, a turquoise color. Thank you very much. Yes, turquoise. So I'm going to do it one more time so you can see what happens exactly. There's a collision. Energy of the collision goes into the electrons. Electrons go up, come back down, and they emit a light. So let's do it and find out again. There we go. Collision. Electrons are going up, coming back down, and give you two photons. These two photons match the two emission lights in the spectrum of hydrogen. So this red light is caused by the electron coming down from the third to the second orbit of the hydrogen atom. This light is the electron in the hydrogen atom coming down from the fourth to the second. We know exactly what happens when the electrons in the hydrogen atom move around. In this case, we have an emission spectra. And I'm going to show you a little video so you can see exactly what is causing it.
I have a question.
Yes, this is Mr. Farmer.
Yeah.
Yes.
Why didn't the electrons fall back down to the ground state?
Okay, that's an excellent question. As usual, Mr. Farmer, you always ask the best questions. It will, but we don't have enough patience. We're going to go to the next GIF. So what happens here is the electron will go to the first state and give you ultraviolet. But since we're not going to be able to see the color of the ultraviolet, that's why I didn't include it here. But you're absolutely correct. They always go all the way back down to the ground state. You're absolutely correct. I was just showing you the two lights here, the red and the turquoise, and the spectrum that is visible to our eyes. That's all. Does that answer your question, Mr.?
Yeah. Thank you.
My pleasure. Thank you for asking. All right, so this is collisional excitation. A lot of the light that you see in the sun is caused by collisional excitation. You can imagine if there's more atoms and the atoms are moving faster, there'd be a lot more collisional excitation. Like if we all were in the classroom, we all got up and start running around, there'd be some collisions. If we all got up and start going really fast and turn off the lights, there'd be even more collisions. The faster we move, the more collisions we'll have with other people in the classroom. Same with the atoms. They have more collisions when they travel at a higher speed and when there's more atoms. All right. Now, here, I have to go back here. I don't know why this thing doesn't happen. Okay, so watch out now. We're going to have free electrons. A photon hits an electron. electron moves to another atom, and then it gives off a photon. So let's do this again. And we say the free electron combines with another atom as now bound electron. So this is a bound electron, but it was free before. I'm going to show you this a few times so you can see what's going on here. This is not it here. Free electron all by itself. It joins an atom. So a photon came in, hit the electron got popped, and it became a free electron. Free electrons are free of their atoms. They're not bound to their atoms anymore. They're free. There's a lot of free electrons coming from the sun. We call them free electrons. The electricity in your wall is a free electron. It's not associated with any proton. So electrons that are not associated with any proton, they're not associated with any atom, they're called free electrons. So let's watch it one more time. Bang, free electron. Now it joins an atom and it gives up light. Now, a good example of this is when the electrons come from the sun. This is called solar wind, when the electrons come from the sun, solar wind. Protons also come from the sun. When they hit the atmosphere of the Earth, then the atoms in the atmosphere of the Earth, some of those atoms in the atmosphere of the Earth, they take in those free electrons. And when they take them in, the electron has to give a photon. That photon represents the difference between the energy of a free electron and a bound electron. A bound electron is the one that is in an atom. So this guy just was a free electron. It joined another atom. Now it has to give up the extra energy that it had as a free electron. So light comes out. Another example will be your fluorescent light bulb. In your fluorescent light bulb, there's a lot of atoms. You pour in a whole bunch of electrons in there. How? You connect the fluorescent light bulb into electricity. So you pour in a whole bunch of electrons into the fluorescent light bulb. The electrons will then combine with the atoms in the tube. When they do, they have to give up the energy that they had as a free electron before they became bound electrons. And that's called fluorescence or recombination. Let's do it one more time. Here we go. Bang. Lands here, gives off a photon. Recombination or fluorescence. Now, some of the fish in the ocean, they also have electricity and they glow underwater. Specifically, some of them that I've seen way, way below the ocean surface, like a few miles down, they glow. They're called fluorescent fish. They fluoresce. See what else we have here. I didn't make these continuous for some reason, and they don't happen in the Microsoft app. So I got to go backwards and forwards to see it. All right, so here we just have an electron come down in orbit. It came down from the 5th orbit to the 2nd orbit. We know exactly what happens when the electrons come down from the 5th orbit to the 2nd orbit. That gives you this beautiful kind of purplish light. If you get the spectrum of a light, you see there is a bright line here. This bright line is an emission line. This emission line happened when the electron came down from the 5th to the 2nd. If the electron was in the 2nd orbit, the 3rd orbit, and it came down from the 3rd orbit to the 2nd orbit, like this, then it sends off a photon as well. That photon will be this one here, red. So when the electron comes down from the 5th orbit of the hydrogen atom to the 2nd orbit, it gives you this beautiful purple. When it comes down from the 3rd here to the 2nd, it gives you this beautiful red. When it comes down from the 4th to the 2nd, it gives you this beautiful turquoise light, like that. So that explains these lines. This is a spectrum called emission spectrum of hydrogen. If you have a hydrogen tube and you pour a whole bunch of electricity in it by connecting it to electricity, then you get all of these lines. Every single one of them happens. I'm going to show you that in a movie in a few minutes. Okay, let's see if we have anything more. All right, so now we have the sun here. Let's say this is a continuous spectrum. The sun gives you a continuous spectrum. It's got everything in it. Reds, blues, greens, purples, everything. All the light is here. Now, if the light of the sun goes through this cloud of gas, some of the atoms here, they do absorbing. Some of the atoms, if they're really high energy, they do emitting. So you get two spectras here. You get a spectra we call a bright spectra or emission spectra, and they happen because the gas is hot and the electrons join the atoms and they give you bright lights. On the other hand, when the light goes through the gas and the photons take the electrons from a lower orbit to a higher orbit, in other words, absorption, then is gone. In its place, we get dark lines. That's called absorption spectra. So here, as an example, this black line here is produced by an electron in a hydrogen atom. When it's in the second orbit and goes to the third orbit, it absorbs this red light. Very, very specific red light. In helium atom, the electrons are not exactly here, the electrons are here. So this is caused by the electrons going from the second to the third orbit of a helium atom. This absorption lines are called the signature of God because no two orbits have exactly the same energy level. So we can tell exactly what's present. Imagine this light of the sun goes through the atmosphere of Mars, and then it reflects back from the surface, and we see it on Earth, and we get the spectrum of Mars. What we see is a whole bunch of dark lines. These dark lines tell us what was absorbed in the atmosphere of Mars, so we know exactly what's present in the atmosphere of Mars. That's how we know what's in the atmosphere of Mars. That's how we know what's in the atmosphere of Jupiter. That's how we know it's in the atmosphere of a star far, far away. We can tell exactly what the star is made of. The chemical composition becomes obvious. We also do this in the lab to see, like CSI, to see what kind of a poison killed some guy. Same thing, right? We can get the same dark lines that present atoms. Electrons in the orbit of an atom. Okay. Time for a movie now. Let's show you guys a movie. Okay, let's see. Where is my movie here? Oh, here it is. Great. I hope this is loud enough for you to see. All right, this is called the Fabric of Cosmos and Reality, basically. Search for reality.
So how did we discover them? These strange laws that seem to contradict much of what we thought we knew about the universe. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun. How a ball.
By the way, did you guys recognize that formula? Anybody recognize that formula for a point?
We thought we had it pretty much figured out. The rules that govern how planets orbit the sun.
Yeah, that's
Inertia? Or
Relax. Speak. Take it.
that's the formula we were using for strength of gravity.
Gravity, that's right. Force of gravity is equal to G, gravitational constant, m1, m2 divided by distance to the power of 2. That's right. Gravity.
How a ball arcs through the sky, how ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense, until about 100 years ago, when scientists were struggling to explain some unusual properties of light. In particular, the kind of light that glowed from gases when they were heated in a
Okay, so this
glass.
gas is hydrogen. Let's say this is a hydrogen tube. It's the same as your fluorescent light bulbs. And he just put it in the tube holder that has electricity going through it. So it's going to turn on the electricity, pour in the electrons. The electrons are going to combine with what's in there, and we're going to get transitions between one orbit and another. Let's take a look.
2. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smeared kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who at the beginning of the 20th century were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths. And that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. That's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising is that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Think of your daily life. When you eat food, you think your food is quantized? You think that you have to take a certain amount of minimum food? Food is not quantized. But the energy of the electrons in an atom are quantized. That is very mysterious, why that is.
As mysterious as it might be for tiny particles in an atom to act this way, the evidence quickly mounted showing that Bohr was right. In more and more experiments, electrons followed a different set of rules than planets or ping pong balls. Bohr's discovery was a game changer. And with this new picture of the atom, Bohr and his colleagues found themselves on a collision course with the accepted laws of physics. The quantum leap was just the beginning. Soon Bohr's radical views would bring him head-to-head with one of the greatest physicists in history. Albert Einstein was not afraid of new ideas. But during the 1920s, the world of quantum mechanics began to veer in a direction Einstein did not want to go. A direction that sharply diverged from the absolute definitive predictions that were the hallmark of classical physics.
If you asked Einstein or other physicists at the time what it was that distinguished physics from all kind of flaky speculation, they would have said it's that we can predict things with certainty. And quantum mechanics seemed to pull the rug out from under that.
I want to show you this later. This is a pretty incredible thing, but I want to show you guys later. Any questions so far, you guys? Okay.
Some of it's a bit over my head, and it goes very fast. So,
what? Tell me, what is it over your head? What is
that
it?
whole, I don't know. I just don't understand the quantum leap and.
Oh,
Yeah,
you
I have a question.
nobody understands the quantum leap, Linda. Quantum leap just means, you know how I showed you the electrons going from one orbit to another orbit? What it's saying is that they don't actually move, they disappear and they reappear in the other orbit. There's nothing to understand. It's just a miracle. Nobody knows how they happen. Is that what you're talking about?
Yes.
Yeah, nobody knows. It's totally mysterious. Nobody knows. So you're in a good company.
Part that I don't understand is that in those test tubes where they were testing the electricity going through the hydrogen tubes, if the light that was emitted from the change of electrons, like, since that's one movement, why does it stay there? Like, why is it constant light when you're looking at it when all it is a quick change in electron?
Because, yeah, you have to realize, if you look at, can you take a look at your fingernails for a second, Noah? Yeah. There's 100 trillion atoms in that fingernail, buddy. So we're not talking about, like 14,000 electrons. We're talking about 14 trillion electrons. So if half of them don't want to do it, the other half do it. It's all chance. So what it's telling you is universe is not deterministic, but it's based on chance. Einstein couldn't accept that the universe is based on chance. That's why we do all this statistics, because only through statistics we can understand how the electrons work. Like for example, if you say an electron is in the second orbit, right? Well, not necessarily. The electron doesn't have to be in the second orbit. We can't even figure out where the electron might be. So I'm giving you a very, very simplistic view. Electrons continuously move. Now they're in the first orbit, now in the 15th orbit. You know what? They move continuously. They're not in the one place. But here's the thing, Noah. You're made of atoms too. How come you're not acting weird? How come you're not jumping around? How come you don't disappear from your room and reappear at Mesa College all of a sudden and then back again, That's a big question. That's a philosophical question. If we're made of all this weird stuff, how come we're not acting weird?
So small that it all.
You think so? Well, here's the thing, Noah. There's a possibility that you could walk through the door, like right now, your front door. You could walk right through the door without opening it. The possibility. But it's 1 out of a trillion, right? So if you go through the door 1 trillion times, one time you could go right through the door. There's a possibility that the entire universe came from nothingness. Nothing at all. In fact, everything that you see in the universe today was not there at the beginning. There was nothing, not even space. And yet there was a universe. So the only thing that was there was the laws. The laws allowed the electrons to tunnel. Electrons can tunnel, go right through the door. It's called tunneling. So an electron is here in my room right now. The electron can be in your room right now, Noah. Same electron can be in your room in a jiffy. Doesn't matter where in the universe is. Not only that, an electron can disappear in my room, reappear in your room, not now, but tomorrow morning. That's what electrons do. That's what quantum physics is all about. This magic. It's not something that we understand. It's just that we follow the laws and how they work. That's all. Yeah, it's pretty weird.
I'm thinking that just as equipment to see more light has been invented, that at some point some equipment could be made that can see more, and it might see the movement of the electron.
Well, here's the thing. They move so fast that you have to catch them. And you'll never be able to catch them because as soon as you want to see them, you put light on them to see them, but you put light on them, they move.
Mm.
So until the end of the universe, nobody is ever going to be able to take a picture of an electron. Because the electron is going to see the light and move as soon as it sees the light. And pictures that you take are based on sending the light and getting a reflection or something like that, right? So we'll never be able to see an electron, ever.
I have a question.
Yes, please.
I have a question, Professor.
Yes, please.
When an electron is in a higher orbit and it jumps down to a lower orbit, what determines which lower orbit it's going to jump down to?
Well, that's a very good question, actually. That's the thing. It's going to be based on statistics. It could go from the fourth to the second, or from the fourth to the, to the first. We don't know. It can do whatever hell it wants to do, but we can tell you the possibility of it happening maybe is 56% is going to go to the second orbit, 44% is going to go to the first orbit. That's all we can do. Let me show you this. Maybe I'll spend a few minutes showing you something that will explain it a lot more. So for now, let me just go over temperature real quick, okay? Then I'll come back. So you guys remember what temperature is? Temperature is basically a measure of how fast the atoms are moving. Temperature is the kinetic energy, right? It's the measure of the average kinetic energy of the gas. That's what temperature is. So the faster the gas moves, right? Like this is hot, hot, hot. The atoms are moving very, very fast. That's what temperature is. Temperature is basically how fast these atoms are moving. It's a measure of how fast these atoms are moving. Now, if they go slower, it won't be hot anymore. Now it's warm. Now it's cold. Remember this, please. If you forget everything, remember the temperature. When I say high temperature, we're talking about how fast the atoms are moving, right? It has to do with the speed of the atoms, how fast the atoms are moving. All right. Now, in a solid, it's a different story. Remember, in a solid, the atoms are in a crystal. And I'll show you the crystal in a second. So they just move around very, very tiny, tiny, tiny amounts. In the universe, there's 4 states of matter. Solid, which I just showed you, they're in a crystal lattice like this. So in a crystal, they vibrate. That's the temperature of a solid. In a liquid, they move past each other. They're chemically bounded to each other. So this bond between oxygen and hydrogen to make water, that's a liquid, right? So this liquid, they kind of glide past the other atoms. And they're stuck together because they share an electron orbit. We're not going to talk about liquids because there's no liquids in space. So this is the one chance I get to talk to you about liquids. This chemical bond means that, let's say, hydrogen and oxygen, they share their electrons. And that's how they get stuck together in a form of H2O, like that. But then you boil this water, and they start moving faster and faster. As the temperature of the liquid goes up, they move faster and faster. On top, they have a chance to escape when they reach escape velocity, which means they're moving fast enough, they overcome their chemical bonds. When they overcome their chemical bonds, they become gas. Once they become gas, they can move around anywhere they want to go. In this class, we don't even talk about gases very much. We talk about plasma, which is a fourth state of matter, because the stars are made of plasma. Plasma is ionized gas. So the gas can be negatively charged, positively charged, or what have you. Charged gas. So a single proton is hydrogen. The sun is made of a single protons. Inside the sun, the electrons and the protons, they don't even talk to each other. They don't even go by each other. Electrons party by themselves. An ocean of protons party by themselves. So the sun is plasma, ionized gas, positively charged gas, right? That's what we're going to be talking about, positively charged gases in the sun. Now, there doesn't have to be any motion at all. If there's no motion, we say that's absolute zero. And we call that 0 degrees Kelvin. So Kelvin is one way to measure the temperature. Remember, temperature is measuring motion, right? So 0 degrees Kelvin is Kelvin temperature, which we use for science. It starts at absolute zero. 0 degrees Kelvin is absolute zero. It also is minus 459 degrees Fahrenheit. Nothing can get colder than minus 459 degrees Fahrenheit. This is centigrade, minus 273 degrees centigrade. Nothing can get any colder than that either. At 273 degrees Kelvin, water freezes. 0 degrees centigrade, water freezes. 32 degrees Fahrenheit, water freezes. 212, these are all at sea levels. 212 degrees Fahrenheit, water boils. 100 degrees centigrade, water boils. 373 degrees Kelvin, water boils. So it's just a scale for measuring from 0 degrees, absolute zero. So here, absolute zero is 0 degrees Kelvin, right? Like that. Okay, so we have 7 minutes. I'd like to show you guys something for 7 minutes. And this is going to blow your mind because, well, it blow your mind. Let's see if you guys can even try to guess what's going on here. Nobody's ever able to understand what's going on here. Maybe you guys can be the first person. You guys are ready?
One test in particular, which would come to be known as the double slit experiment, exposed quantum mysteries like no other. If you're looking for a description of reality based on certainty, your expectations would be shattered. We can get a pretty good feel for the double slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit. The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller. You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing. Waves. Waves do all kinds of interesting things. Things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes and what's known as an interference pattern. So how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave? Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave. A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. A rock is an example of a particle. An ocean wave is an example of an ocean wave. And now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described. Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave. That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there?
All right. Did you guys catch that? Now it gets much more weird. Think about it. So we have two slits, right? You have two openings. One electron can go through both of the openings. That's right. A single electron can go through both of the openings. But guess what? If you get a camera or you get an observer, it won't happen. The electron will go through one opening only. So the observer, the act of observing, changes the experiment. Is that weird enough for you now? So that's what we're dealing with. And guess what you guys are? You guys are all the jumble of possibilities. You're made of this stuff, right? So you're all magical. Every single one of you is magical, basically, right? You're all magic. Now, they tried this, you know. I've tried this experiment. We put the camera. I don't even have a person, just a camera. When I put the camera, you could see the electron going through one of the openings. Take the camera away, the electron goes through both of the openings simultaneously, like a wave. I don't know. It's just the way the universe is. Don't ask me how, but it is the way it is. Nobody knows the answer. It's a pretty impressive thing. All right.